So I think we can begin. So our first speaker of the afternoon session is Kevin Costello, who will be talking on supersymmetric, holomorphic, and topological field theories in dimensions 2 and 4. So this is actually the first lecture of the 3-lecture series. So you will hear more on that tomorrow, and your third lecture is on Monday? No, it's not. On Saturday. Okay.
Thanks very much, Sasha. I think my title is actually a little misleading. I'm not sure. I think I'll have to be introducing other things before I get to talk about supersymmetric theories. So that might have to wait in the last lecture. Okay, is the mic on? Yeah. Yeah, it's on. Yeah. Is that better?
Speak louder.
Okay, so, as people, suppose we have a manifold X, and a very familiar operation people do in geometry is you might consider some moduli space of solutions to some elliptic equations on X. So we call this, something like an elliptic moduli problem. So for example, you might consider, e.g., if X is a 4-manifold, an example of an elliptic moduli problem might be G bundles on X. The connection satisfying whose curvature is self-dual. Maybe another example, C is a curve, Y is a complex manifold, then space of holomorphic maps is another.
By curve, you mean?
Oh, Riemann surface.
Riemann surface.
Yeah, my algebraic geometry background is showing through.
So there are the equations that have the homological.
Exactly, yeah. So it's a very familiar thing that people might be interested in doing in geometry is you might take some manifold X, consider some system of elliptic equations on it, look at the moduli space of solutions, perform some integral over that to get invariance. So for example, kind of cartoon of Donaldson theory. If we look at this first example, then the Donaldson invariants are some kind of integrals over M of X of some natural cohomology classes. So this is clearly, a ridiculous cartoon. There's a lot more to be said than this. And similarly, with this example, you do the same thing. You end up with Gromov-Witten invariance. here a moduli space of holomorphic maps, some natural cohomology classes. And this should give you the Gromov-Witten invariance of this complex manifold. Okay, so the story I'd like to explain is the following. So the first part is to any elliptic moduli problem like this. I'll give you a precise definition of elliptic moduli problem in a little bit. I'll show you how to associate a classical field theory so there's this nice class of classical field theories. Anytime you write down a system of elliptic equations, or think of any geometric context, this kind of thing is very common. You get a nice classical field theory.
Excuse me, I don't want to make you say what you're going to say detail, but just one sense about what you mean by classical field
theory. Actually, I think I spent a lot of the lecture explaining this. But according to the Badlin-Bulkowski formulas of a classical field theory is some space with a symplectic form. So this will be interpreted as some geometric object. So really, we're going to interpret classical field theory as being an elliptic moduli problem with some extra geometric structure. So in the second lecture, I want to talk about the notion of quantization. Well, I'll say a little bit about what it means to quantize, and show that quantization of this theory gives, well, a volume form on the moduli space. And I suppose my third lecture, I'll be explaining how many theories of interest in mathematics fit into this formula. So I think I said in my abstract that I wanted to explain how you can see the A and the B models from this setup, and also some twisted versions of supersymmetric Yang-Mills theory, like in this recent work of Kapustin and Witten. So I think I'll spend my third lecture explaining that picture. So before I get on to the content of this lecture, just a little I just might want to say a little bit about what the volume form for these two examples means. So if E is an elliptic curve, Y is a complex manifold, 1. Well, we have this moduli problem of holomorphic maps from E to Y. So, if the second character of Y vanishes, then this quantum theory has a unique quantization. And therefore we get a volume form in this volume of this moduli space is something called the Witten genus of phi, the elliptic genus. So this is, to mention, I was maybe mentioning this to point out that this elliptic genus is a modular form. It depends on the actual elliptic curve, where it lives in the moduli space of elliptic curves. So that's really in contrast to Gromov-Witten invariance. In the more familiar story, where we do this kind of homological integration, I integrate natural cohomology classes over the fundamental cycle. If I change my elliptic equation a little bit, I'm going to get the same answers. So if I change my curve, the Gromov-Witten invariance won't change. So that's the point of that story. But this is a bit different in that the volume form you see reflects the geometry of the space we're working on. And so I have some work in progress about this example. It acts as a four manifold. And again, MX is the anti-self-dual G bundles. Then I think I can show that again, in this case, the theory exists in quantization. And that the volume of these moduli spaces, it's again something interesting, which depends on the conformal structure of X. And it's something, it's more closely related to physics, and that's going to be some limit of Young-Mills theory. Okay, so this was just an advertisement that you do get something interesting in this story. Okay, so
Can I ask you a question? Are 1 and 2 sort of math statements? I mean,
yes.
Okay, so if I understood your definitions of all those words, it would actually, it's not just like a metaphor, it's an actual theory.
Yeah, there's so I'll spend most of the second lecture, I think, explaining what the word quantization means. Okay, so most of this lecture, I think, I want to spend some time.
But the volumes that you actually get are always finite because others are not.
Oh, okay. That's an excellent point. In this example, I know I'm lying a little bit. We're only looking at the degree 0 holomorphic maps, and the volume is finite. In this example, I don't know how to complete the volume. I just have the volume form. It may blow up in the boundary. Okay, so I'd like to say a little bit about what I mean by an elliptic moduli problem. So we should all have an intuitive idea of what it means to have a system of symmetries to some elliptic equation. But it's going to be helpful to formalize that definition. Well, of course, if you look at these two examples, you'll realize that, the moduli space of solutions of the self-duality equations is kind of badly behaved. It's not of the expected dimension, very singular, so on. And same for the moduli homomorphic maps, it can be very badly behaved. So, often the actual moduli space is badly behaved. So, but there's this philosophy which is well known to many people, that the hidden smoothness philosophy. I think this is really, I certainly learned it from Koncevich's paper where he introduced Witten invariance, or Koncevich-Riemann invariance. I don't know.
Excuse me, Kevin.
Yeah.
This is my birthday, let me treat myself. There's a seminar in Israel at the Millennium, McPherson gave this long, beautiful talk about singularities, and Savage came up next and said, John said, there are no singularities.
Yes, yeah. Yeah, I kind of agree, right? I mean, if you treat it correctly, everything is smooth. Well, the same smoothness philosophy says that if you treat in the derived world, some world of derived or more homological geometry, these spaces are really smooth. Okay, so now, if you're a very ambitious person at this stage, you might say, let's develop some big general theory of derived C infinity stacks, yada yada. It's all very complicated. It becomes even more complicated because of compactification, and you might run into polyfolds and all this craziness. But I'm lazy, so globally derived geometry is kind of difficult. But locally derived geometry is really easy to describe. So instead of trying to work out a general theory of your elliptic moduli problems, I'll work out one at a formal level. So what we'll do is we'll give a definition of that. Formal means you're looking very near in the infinitesimal neighborhood of a particular solution. Derived. So why is the formal story easier? Well, it turns out the formal story is actually easier because it's basically linear algebra. So there's something which maybe we could call the fundamental theorem of deformation theory. And it says that formal pointed, so pointed means, of course, there's a specified point, derived spaces. Well, there is a whole theory of derived spaces in which this statement is true, but I don't really want to give you the general definition. Are the same thing as differential graded V algebras. Or if you're somebody who likes homological algebraic structures, you can use L-infinity algebras.
And go over the Maxwell numbers here?
Oh, of course, yes. Yes. Well, that's an excellent point because, of course, this really is some generalization of rational homotopy theory. I mean, derived geometry includes, on one side, homotopy theory, and on the other side, algebraic geometry. So formal derived geometry, should include rational homotopy types. So we can give some idea of why this is true. Well, I have some names. as I said, I think this really, the heart of this statement goes back to rational homological theory. But in the early 90s, it was developed maybe in a more context of algebraic geometry by people like Greenfeld, Levine, Hansevich. And there's a precise theorem of this form due to Hinich in the mid-90s. And there's a recent paper of Jacob Lurie's ICM talk, which is actually a really good read. It explains these ideas very clearly if you're interested, which generalizes things even further. Okay, so what's the basic idea here? Well, so functions on derived spaces are commutative GGAs. So functions on formal derived spaces well, there should be some kind of completed co-element. So, if A is one of those, without loss of generality, we can choose a free resolution. Our inset is equivalent to something of the form, the completed symmetric algebra on some vector space with the differential well, taking the completed symmetric algebra, we only need to define the differential on the generator. On the generators, here's B is some graded vector space. And yes, actually, this whole picture is something I learned from Dennis when I was young. Completed, yeah. So now what you say is that whereas the Lie algebra is just V dualized. And the Lie structure is given by the Taylor expansion of the differential. So, the algebra okay, so it's in fact a Lie infinity algebra. So the maps En from the Taylor terms in my differential so these are maps defining an L-infinity structure. Okay, so for example, L1 is a differential 2 is the bracket. And so on. Okay, so this is a story which I think is pretty central to people who think about homological algebra. And a classic example, of course, is if I take A to be the minimal model of a space, then this Lie algebra is the homotopy groups of the space appropriately computed. Okay, so according to this hidden smoothness philosophy, as I said, every formal derived space is represented by a Lie algebra, or an L infinity algebra if you prefer. So we've seen roughly how this goes. You know, functions should be this completed equivalent algebra. You replace this by an L infinity algebra. But if you want something a bit more concrete, so if G is, say, a BG algebra, and suppose that R is an Artinian ring, and M is the maximum ideal.
Can you recall what that means?
Of course, so that it's, or you know, go over some field. It's some finite dimensional algebra, and the ideal is nilpotent. So the basic examples you should bear in mind, you know, I join some parameter t and set the n power of it to 0. Well, okay, so if I have one of these guys, which I should think of as a little thickened point, you might ask, what are the maps from that thickened point to my formal moduli problem? Well, the idea is that G defines a formal moduli problem. That you say that Holmes from spec or to this moduli problem, I call it M sub G, Holmes preserving the base point. You know, this is a base point and this is a base point too. They should be the Morrow-Cartan elements of G tensor the maximal ideal. And to be completely precise, there's some equivalence relation, but that's best formulated as saying that this is naturally a sufficient set. It's a little fancy. But let me just remind you what Morrow-Cartan means. This is the set alpha in G of 1, G tensor M, satisfying the equation B alpha. Pointed maps. This is
Pointed the plus sign.
yeah.
What is M sub G?
It's what I'm calling the formal moduli problem associated to G.
And the on into it all.
Yeah.
Oh, I see, that's being defined.
Exactly. So if you want to be a little more fancy, then you would say, or might be some differential graded Artinian ring we should treat this guy as a simplicial set. This is what people like Jacob Murray or Tony Fitzalzi would call a formal derived space. Pardon? Rewind.
Sorry, can you say what the gauge group actually looks like when you say simplicial set?
Okay, so this is the zero synthesis.
Well, this says the zero.
Yeah. I don't know. Losing this blackboard. It's not coming off.
Do something magic in this one.
Yeah.
Never happened.
What was it?
I said it's like it never happened.
Uh-huh. So yeah, in the simplicial formalism, these are the zero simplices. And so the n simplices. Actually, again, this is another idea I learned from. Whenever you're considering solutions to any algebraic equation, you can make it into a simplicial object by considering families over cochains on the n simplices. And another idea I learned from Dennis, although he denies. Inventing it. You just do this. You just consider families of Mark-Markov elements, or parameterized by this forms of the simplicial set, and this clearly forms a simplicial set. And if you work out what pi 0 of this guy is, this is what people would normally call Mark-Markov elements of the gauge equivalence.
So in that setting, you have a differential in M.
Absolutely, yeah. So in this way, if we wanted to be fancy, as I said, in this way we get a functor. So Ng is a functor from differential graded arcing rings to simplicial sets. And if you look in the sophisticated literature on what derived algebraic geometry is all about, this is what a derived space is defined to be. So, what a derived space is defined to be, it's a functor from GG rings to simplicial sets. Okay, so this thing is a little bit aside. So I wanted to use this statement, the fundamental theorem of deformation theory, to give a definition of elliptic moduli. And now I hope you can see where we're going. What was it?
I think the blackboard is that way.
I think you have to do one then the other. That was my problem with the middle one. Okay, so let's make a definition. Our definition is going to be of an elliptic Lie algebra, e.g. Lie algebra. So on a manifold X, so it's a graded vector angle. I'll call it L on X, and these sections I'll call, say, curly L. structure? Well, we just want that the global sections is given the structure of a DGB algebra. Where, so firstly, the differential I want this to be, the word elliptic is going to be some condition on the differential. I want this to make this cochain complex into an elliptic complex. Will be denoted, sorry.
What is an elliptic complex?
Okay, yeah, I'll tell you in just a second. I'll tell you the inner axiom first. Oh god, is this another unusable password?
It's because you wrote on it while it was wet.
It was wet.
Oh, that's what it was. Oh well. This will cause problems later on, might do. So the second property is that the Lie bracket is something which is called a bidifferential operator. So let me say a little bit about what this means and what elliptic complex means. So this means if I have two sections of this vector bundle, then I can look at their bracket and I can evaluate that that's at some point in the manifold, and that's an element of the fiber of my vector bundle there. And to be a bidifferential operator says essentially that this guy, so the axiom is that phi psi brackets x only depends on the Taylor expansion phi and psi of x. In other words, we get it by differentiating these guys a bunch of times and then find something linear.
You mean a finite jet or the whole Taylor expansion?
Finite jet depends continuously on the jet.
But we don't restrict the degree.
No, no restriction on the degree. Okay, so really, before I say what the complex is, I just say that you can, of course, generalize this definition very easily to use the L infinity world. So you can easily generalize that follows from the fact that all of the maps are differential operators.
As in some sort of locality.
Exactly, yeah.
Scott, you mentioned the elliptic complex was.
Yes, yeah, I did.
So when you say sections, are there smooth sections?
Smooth sections. So, the basic example is going to be the derived complex. Okay? So of course, if you have a or maybe the Dalton complex of complex manifold.
Maybe the values of the vector bundles must be the vector specific.
Exactly, yeah. So that's what we're going to be doing in a sec. You values of the vector bundle, you get one of these elliptic alphas. So, of course, the derived differential is not an elliptic operator. The kernel of the derived differential might be infinite dimensional. The characterizing one important property of an elliptic complex is that if we have, on a compact manifold, an elliptic complex is a finite dimensional cohomology, just like on a compact manifold, an elliptic operator has finite dimensional kernel. So, the formal statement, what an elliptic complex is a little technical, so maybe you should bear these examples in mind. Formal definition is it's a graded vector bundle of X a differential operator D well, anytime I have a differential operator, I can take its symbol. This can equal 0. Look at the complex. Now just the complex of vector bundles on the cotangent bundle minus the 0 section. Where I pull back the graded pieces of my vector bundles and the differential is given by the symbol of this operator. This complex has to have 0 cohomology. So it's contractible. So as I said, this may be a little unilluminating, but we've seen two basic examples. Another example is that a two-term elliptic complex is the same thing as an elliptic operator.
It's saying the same as B plus B star, so it's elliptic in that sense.
Yes, but we haven't to define B star, you use a metric and everything.
Kevin, do you want 0 homology in all degrees, or do you want
It's the exact sequence.
It's an exact sequence, yeah. 0
not
cohomology.
contractible, it's actually empty?
And ozone?
Yeah.
Contractible
No
means the form.
cohomology conditions there. It's just exact.
Yeah.
Exact.
Yes. So a two-term elliptic complex is the same thing. D is an elliptic operator. because to be an elliptic operator means that the symbol of it is an isomorphism. To be an elliptic operator means the symbol is an isomorphism away from the zero section. Actually, use that word now.
Could you take a moment to do a kind of classical example, I think, for Aristotle's theory of design?
Yes, exactly. I was just about to do that.
When you do that, could you maybe remind some of us what the symbol of an operator is? Some of us that don't know the analysis.
You know, I'm not sure.
It's the tensor you get by looking at the highest order piece of the differential operator.
So you think of d by dx as a function of the cotangent bundle. So it gives you some mapping of vector bundles of the cotangent bundle. But as I said, I mean, if you're not familiar with that language, this is really unilluminating. But the key property is that if X is compact, then the cohomology is finite dimensional. That's like just like if X is compact, then the kernel and co-kernel of the elliptic operator are finite dimensional. So let's give some examples. Suppose that X is again.
I mean, there is an interesting math point, right? That you'd like to do everything to infinity. In fact, the image of the operator's closed is a non-trivial point. So when you find homology, you take it out the break.
Yes.
And that's kind of the deep point where you need all this care.
Yes, absolutely.
Yeah.
I agree. Yeah, is that true when you can order non-compact?
I don't know. I don't know what's true in context.
Me too, yeah. I always wanted to know, but so X is a manifold. Let's say I have a vector bundle. With flat connection. You can ask, well, I can look at the formal elliptic moduli problem. Yeah. Formal moduli problem of deformations of V and nabla. Okay, so I can ask what is the corresponding elliptic V algebra? Where, well, I just take forms on X.
Forming among the set of flat connections.
Yes, so we're deforming V as a vector bundle and nabla as a flat connection. So, of course, V can't deform, so it's the same as deforming nabla against equivalence. So this corresponds to in the algebra, forms on X with values in the endomorphism bundle of V. Well, differential arises from the flat connection coupled to the usual way to the Durand differential. And of course the Lie bracket is the only thing can be it's a combination of wedging of forms and bracketing of matrices. So the derived comes from the fact forms and the Lie structure on N. I suspect I'm not going to get really far. That's okay. So why does this correspond to deformations of D? And now, well, I need to tell you how Mark-Cartan elements in here relate to forming this pair. So if I take or to be the ring, say, K or T modulo T cubed, so the maximum ideal, and spanned by T squared, then the Mark-Cartan element of this thing is called Al. Something of the form T alpha plus T squared beta, such that this is closed, and the failure of this guy to be closed, sorry, alpha and beta are in under 1. The failure of this guy to be closed okay, what does this mean? This means precisely that if I take my original connection and I add on this expression to it, it's still flat. So this is really the classical example of deformation theory. Deformations of a flat connection are Mark-Cartan elements of this Lie algebra. And if you work a little harder, you'll see that gauge equivalences, I can change this deformation by some bundle isomorphism, and that will correspond to homocopies in this official set you wrote down, Mark-Cartan elements.
V is built into L, so how do you change V?
Well, V can't deform, right? A vector bundle has no infinity deformations.
So, I mean, is there any kind of analog in this language of the fact that you can have the moduli space actually has an unusual property? So that as you change
Yes.
as you change the ring,
Yes, so what you can say is, so what we've kind of sketched is that the value of this moduli space on any orphan ring is, flat families of vector bundles with flat connection over X across the spec of that ring. And that's true. I mean, that's.
So really, you're looking at it refer into moduli system.
Exactly, yeah. And we're saying, well, we defined it in this algebraic way, but actually you can also identify it as literally the moduli space of flat connections, with jets of flat connections.
So in particular, if you divide that by T to each end here, the computation would be more complicated. If you just chose to give it to the CCAC.
Yeah. But it's, I mean, it's kind of clear how it should continue. It's just equivalent to this statement that this whole thing is flat.
Is there a nice interpretation if R is graded? I mean, if R is, maybe as it is graded.
Yeah, I suppose then, for example, if R has stuff in negative degrees, then you'd be forced to include forms in positive degrees bigger than 1. And then you'd see something like a superconnection. So what we're seeing, I mean, but you really need to include that stuff, because if you think of what are the roles, you know, omega 1, this is deformation of the connection. Omega 2, this like imposes the equation of flatness. Omega 0 is the gauge equivalence. But the higher stuff, these need to be included to make the complex elliptic, for instance. But they're really kind of higher versions of being flat. Yeah, and as I said, if you consider this whole derived moduli space, it's very close to what Quillen called a superconnection. Okay, forward. I'm almost out of time, so I suppose what I should do is give you a couple more examples, and then next time I can explain what classical geometry is. So the example is almost identical. X is a complex manifold. This is a holomorphic vector bundle. Then this with the coupled D-bar operator. This is the elliptic Lie algebra, which controls deformations of this complex vector bundle. Okay. And not deforming X. We're keeping X fixed. It's just deforming the bundle. And you can see that just because the only things that can really move is the D-bar operator on E. And the possible ways the D-bar operator can move is by a 0-1 form of the values of the endomorphism bundle. And the same argument that applies. So maybe self-duality equation. X is a 4 manifold. B is a vector bundle connection nabla with self-2 curvature. And the self-2 part of the curvature vanishes. Then again, this is another nice elliptic moduli problem. And the elliptic Lie algebra it looks like the following. Okay, so degree 0, it's just as before, it's the sections of the endomorphism bundle, which we interpret as the gauge group. In degree 1, it's one forms of values in the endomorphism bundle, which are infinitesimal notions of connection. But in degree 2, well, the stuff here is required to impose the self-duality equation. So we just stick in the anti-self-dual two forms with values in ND. And if you work out the Maurer-Cartan equation, you'll see easily that it's deformations of this connection which are anti-self-dual, or just self-dual. Do I have one more minute, or? Okay, so the very last thing I wanted to say is just to observe, to justify the terminology. So now suppose that L is elliptically algebraic. And you can look for, so if OR is, or T modulo T cubed, I could look for the Maurer-Cartan elements. And what do I find? This is the set of elements, things of the form T alpha, that's T squared beta, where alpha and beta are in L1. And these satisfy some equations in the D alpha equals 0, D beta plus half alpha. Okay, so by definition, the Maurer-Cartan elements are things in this form. So why am I writing this? Well, you see that these Maurer-Cartan elements are literally solutions to a system of elliptic equations. Right? So D alpha equals 0. This is some kind of linear elliptic equation. On alpha. And the second term, because I required that this bracket is a bidifferential operator, so again, this equation is some nonlinear system. It's some nonlinear system of PDEs. But the key point is that its linearization is elliptic.
Those two equations decouple. So you first get a linear equation of alpha and then a linear equation of beta for beta.
Yes.
And that's the analog to the classical statement that you have H1 and H2 playing.
Yes, I mean, these two equations these are both elements of H2. They should both vanish. I mean, it's the classical statement is, given a nonlinear equation and a solution, we can try to solve it order by order with some small parameter. And you find first order is in linear space. And that's in quadratic thing.
Well, I'm thinking if you had modeled out not by TQ but by T squared, you had first order equations, you wouldn't have the second equation. So that would be the H1, which is a formal tangent space.
Right. So, yeah, exactly. H1 is a formal tangent space. H2 is a formal obstruction space. These equations are saying that alpha and beta are elements of H1. Right? Alpha is an element of H1, but it's closed.
Right. And beta is something that's in H2. But why don't you have any kind of gauge equivalence would be saying that alphas are up to mod out by
yeah. So we said that this thing, you can think of it as a sufficient set, and you can consider families. And first order, that amounts to modding out by exact guides. But the higher order, it's some kind of nonlinear gauge equivalence. Okay, so I'll stop here, and you can get very far with this formal definition. And next time I'll explain what a task field theory is, and how to construct them, these objects. Oh, so he said, what does it mean that the linearization is an elliptic equation? Maybe, okay, so one way to say it is that the linearization is just like looking at the tangent space for a given solution of the equations. So in derived geometry, the tangent space is always a cochain complex. And we're saying that, that's an elliptic cochain complex, which is... Yeah.
I think we have time for maybe one more question.
If I have a compact manifold and some nonlinear elliptic equation over it, solution to it,
Yes.
do I get it?
Yes. Yeah. So,
Completely general.
yeah, absolutely.
But, and what are the right things to say?
No, it doesn't have to be first order. It just has to be
Yeah.
the quadratic term of your equation to be elliptic. Right. Sorry, not the linear term of your equation is to be elliptic.
Yeah.
What's the question and what's the answer? What's the exchange?
So he's saying, suppose you write down some general PD and you have a solution, and you look at nearby solutions. Does it can be described by this picture? And the answer is yes.
Manufacture whether you should go with the other.
Yeah, exactly. Yeah. And then really, I mean, this is just some way of writing the equations in an algebra.